Okay. This week's tutorial is what I think the most fun tutorial because it only involves, the past couple of weeks we spent time how to pre-process and run the simulations, and now it's actually time to look at the results. So I have opened Paraview, which is an open source software and is capable of high performance post-processing, so you can even run it on a remote high performance computer and do all your expensive post-processing there, and then you can attach to the server and look at your results locally. So it's a very capable software, which can make it sometimes a little bit confusing. But now, in the next couple of minutes, we'll just focus on the most basic features to look at our flow results. And for that, I have prepared a geometry from the vascular model repository. So that's a simple aortic geometry. And up here, we can see the different results fields that we have. So we have the global node ID and global element ID. That's just something that's part of every geometry. And the actual results are the wall shear stress, the pressure, and the velocity. And the number behind the name indicates the time step where this solution was computed. So this would be at the end of a cardiac cycle in this case. And yeah, one common thing is that we might want to look at the pressure. So we select it up here, and then we see color-coded the local pressure. But as you can already tell, there's one issue. So that's the unit of the pressure is the same unit that we used in our simulations, and that's dyne. And usually in a medical setting, you want to use millimeters of mercury. So we'll convert that result. And for that, we can use the calculator filter. And so we'll select the pressure, and we just divide it by 1033. And the result array, we'll name it pressure in millimeters of mercury. Click apply, and then we can see a new field appeared, which we just calculated. And if we select that, we can see that now the pressure is in a range that we would expect for an end systolic pressure. So that's between 76 and 81 millimeters of mercury. So that's the pressure, but of course we can also look at the velocity. So we select velocity up here, and you can see pretty much basically the whole geometry is blue. And when we look at the color scale, that means a velocity of 0. So did something go wrong? No, it didn't, since we prescribed a no slip boundary condition at the surface. We basically prescribed that the velocity is 0 here. And that's exactly what we are seeing. But if we look at the outlets or the inlet, we can actually see that the velocity is non-zero at these places. And there's a big difference between looking at pressure and velocity. Pressure is a scalar value, but the velocity is a vector field. And there is a nice way to visualize that in Paraview with the glyph filter. So when we apply that, and as orientation array, we select the velocity, and the scale array, we also select the velocity. And now we have a slider here where we can basically scale those vectors. So I'm going to make them a little bit smaller so we can actually look at them. And so these vectors now nicely visualize our velocity field. So we can see the inlets, the velocity vectors go inward, and then you can basically trace the movement of the fluid, and you can see that it exits at the outlets of the geometry. So that's one way of looking at flow, but there are several other ways we are also going to look at. So let's say we are interested in local characteristics of flow. There's one part in our geometry where we actually want to analyze the velocity field. And for that, we are going to use the slice filter. So it means we are going to slice our geometry at a specific location. And now we can see this plane that I can move around with the mouse. And so we are going to select Z normal. So that orients the plane in the Z normal. And then I'm just going to reorient a little bit. So we slice it approximately perpendicular to the flow. But what you can also do is, if you know the exact location that you want to look at and you know your normal vector, you can also enter those coordinates directly here, and you don't have to pick it by hand. Okay. It looks like something went wrong here. I think this is under a rendering issue in Paraview. So actually it should just be a slice. Okay, that's interesting. Okay, I'm gonna go ahead, close Paraview, and reopen my previous state. Let's see if it works here. Okay, yeah, this looks okay. So I'm not sure what happened there. So that's my prepared solution. So this is what it looks like when we slice the geometry. So to visualize it, I'm going to make this geometry transparent. So I select solid color and then reduce the opacity. And now we can nicely see where I have sliced the aortic geometry. And now we can look at the velocity just within this one slice. And there's also a nice way to visualize that. And we will use the warp by vector filter. And that basically means that we will displace the surface by the velocity vector. And when we do that, that's what we get. So this is a nice visualization of what the flow profile looks within this one slice. And again, you can see that our no slip boundary condition, the result is that we have a zero velocity field on our boundary, and that means there's a zero displacement on the boundary. So that's the velocity profile. But there are several other ways to visualize the velocity field, since it could be very cumbersome to always slice the geometry at different locations. There's another way to visualize the velocity field in a more global way, and that is the resample to image filter. So what we do here is we take our geometry and resample it. So here we can choose the sampling dimensions. And so basically we create a rectangular grid in all three coordinate directions and basically render our velocity field like a medical image, for example. And this volume rendering allows us to basically view the global velocity field. Yeah. So for example, we can see that the velocity is higher up here where we have a narrowing of the cross-sectional area. And another very popular way of visualizing a velocity field is a stream tracer. And what you do here is we calculate the streamlines. And the streamline tells us what the local tangential vector of the velocity field is. And so if we had a particle of fluid that we would place at the inlet, the motion of that fluid particle would be given by the streamlines. And for that, we select the stream tracer filter, which I have already done here. And for the stream tracer, we select for C-type, we select a point source, and then we get the sphere. And what we're doing is we place the sphere at the inlet, and then Paraview will take care of the integration and basically place seed particles in here and trace their way through our geometry. And what we get in the end are these nice streamlines that start at the inlet and then follow the motion of the fluid to each of the outlets. So that's also a nice way of, a nice global way of visualizing the fluid motion within our geometry. Yeah. Do you have questions so far regarding post-processing? I should stop the recording first. Oh, sorry.